Welcome to Maths with EJD. In this video, I continue to talk about mathematical induction. And the question we have today is what you see right there. We have this claim. We have a claim that 1 over 3 times 3.5. Now, this dot is not decimal point, it's multiplication. So be careful of that. So 1 over 3.5 plus 1 over 5.7 plus 1 over 7.9 plus all that up to 1 over 2n plus 1 into 2n plus 3. Most times when you see dots here, it simply means multiplication, not decimal. So you have to be careful. So, and that is equal to n over 3 into 2n plus 3. So that is the claim. All right. So the next thing to do, like is we do we do the base step. We do the base step. Now the base step, what do we do? You say, of course, on the left-hand side, you have a sum. On the right-hand side, you have a formula. What do you do with the sum? You add things up. And with the formula, you substitute values. So at n equals 1, right? You just pick the first term. That's 1 over 3 times 5. That is 1 over 15 on the left-hand side. So on the right-hand side, you have n is 1, right? So you have 1 over 3 into 2 times 1 plus 3. So that is 1 over 3 into 2 times 1 is 2 plus 3, that's 5. Again, this is 1 over 15. So that is settled. I mean, from here we can go on, but I like to take n equals 2 again, just to confirm what we are doing. So on the left-hand side, for n equals 2, it means you pick the first two terms and add. So you have 1 over 3.5 plus 1 over 5.7, and that is equal to 1 over 15 plus 1 over 35. And the common factor here would be at least 5 is common. 21 times 5, that's like 105. So 15 goes in 105 7 times, I believe. Yes, 7 times. So you have 7, and 35 goes there 3 times. Yep, 3 times. So that is 10 over 105. So that is for the left-hand side. So for the right-hand side, where you have a formula, right? That is, so you substitute 2 into this expression. That is 2 over 2 over 3 into 2 times 2 plus 3. So that is 2 over 3 times 2 times 2 is 4. 4 plus 7, 4 plus 3 is 7. So you have 2 over 21. Of course, this is 5 in 10 is 2. 5 in 10, 5 in 10 again is 2. So it's 2 over 21 in each case. So what do? We say, therefore, the claim is true. The claim is true for the base step. For the base step. The claim is true for the base step. So we can move on to the other part. We have the base hypothesis. Sorry, the inductive hypothesis. That's the next thing. The inductive hypothesis. At this stage, you just assume the claim is true. Assume the claim is true for n equals k. And what that simply means is that you have 1 over 3.5, 1 over 3.5 plus 1 over 5.7 plus 1 over 7.9 plus all that up to 1 over 2n plus 1 into 2n. Sorry, instead of n now you have k. So 1 over 2k plus 1, 2k plus 1 into 2k plus 3, and that is equal to k over 3 into 2k plus 3. k over 3 into 2k plus 3. k over 3 into 2k plus 3. And that goes. So you go back to the inductive, then you move on to the inductive step. So at the inductive step now, you prove finally that the claim is true for n equals k plus 1. So to prove that the claim is true for n equals k plus 1, so you have, so of course, pay attention that this is already equal to this. So anything you add to the left-hand side, you add exactly the same thing to the right-hand side. In addition, you know that at the end of the day, you know you're correct if every k becomes k plus 1. So the k up there becomes k plus 1 all over 3 into 2 into k plus 1 plus 3. So that's like at the end of, once you have 2k plus 2 plus 3, that's, once you have 2k plus 5, then you know you're good to go. And then you can just express it in that way. So let's go. You have 1 over 3.5, 3.5 plus 1 over 5.7 plus 1 over 7.9 plus all that plus 1 over 2k plus 1 into 2k plus 3. Of course, we are dealing with k plus 1 now. So it means you have to also add 1 over, for every k here, you have 2k plus 1. For every k, you have k plus 1 rather. So for 2k, it means you have 2 into k plus 1 in brackets, then into 2 into k plus 1 plus 3 in brackets, and that is equal to k plus 1. I mean, not k plus 1 yet. Okay, for the sake of space, right? I want to bring that down. You know, this should now be equal to the right-hand side, k over 3 into 2k plus 3, plus exactly the same thing you added here, because without that, they were equal. So if you're adding that to the left, you should add the same to the right. So plus 1 over 2 into k plus 1 plus 1 into 2 into k plus 1 plus 3. So all you have left now is to now express this in such a way that at the end of the day, for every k here, you have k plus 1. So let's continue on that journey. So once you do this, you forget about the left-hand side and focus on the right-hand side and resolve it until you get what you expected to get there. So you have k over 3 into 2k plus 3 plus 1 over 2k. So expand this 2k plus 2 plus 1 into 2k plus 2 plus 3. Okay, and then we move on. We have k over 3 into 2k plus 3 plus 1 over 2k plus 3 into 2k plus 5. So we move on, and the LCM here is actually 3 into 2k plus 3 into 2k plus 5. So 3 into 2k plus 3 goes there. You have k now into 2k plus 5 plus 1. All this will cancel, so you just have 3. This and this will go here. So you have 3 times 1, 3. And then we keep going. We have 2k squared plus 5k plus 3 all over 3 into 2k plus 3 into 2k plus 5. And of course, here we can factorize. 2 times 3 is 6. And then we have 5 in the middle. We need two numbers multiply to get 5. I mean, to get 6, and we add to get 5. Of course, since it's all positive, so 5k there will have to be 2k and 3k. So we have 2k squared plus 2k plus 3k representing 5. Now we have 2k plus 3k plus 3 all over 3 into 2k plus 3 into 2k plus 5. And then the journey is on. We can factorize here. 2k is common, so we have 2k into k plus 2 into 2k into k plus 1 rather, plus 3 into k plus 1 all over 3 into 2k plus 3 into 2k plus 5. So that at the end of the day, we have 2 into k plus 1. You know, k plus 1 is common into, sorry, not 2 now. It's better to have k plus 1 is common. So bring k plus 1 out. All of that into 2k plus 3. 2k plus 3. This 2k plus 3 over 3 into 2k plus 3 into 2k plus 5. And this cancels this, right? So you have k plus 1, which is what you expected to have at the top, because for k, you should have k plus 1. And then down here, you have 3 into 2k plus 3. So you have, so this is 3 into 2k plus 5. So that you now have k plus 1 all over 3 into 2k plus 2 plus 3, because you are required to have k plus 1 plus 3 inside this bracket. So you have k plus 1 all over 3 into 2 into k plus 1 plus 3. And that is exactly what you expected to get. For every n you had in the beginning, it has now replaced by k plus 1. So k, you have k plus 1 there. Then down there, you have 3 into 2k plus 3. Then that is 3 into 2k plus 1 plus 3. So, and that is how that goes. So you can say, therefore, the claim is true. The claim is true for n equals k plus 1. So you can now go back to conclude. So in conclusion now, the claim is true for all positive integers, since it is true for n equals, since it is true for the base and inductive steps And that ends that question. So if you have not subscribed, be sure to do that. Hit the notification bell so you can get alerted each time a new video is released. Comment if you need us to solve a problem. Share with others that may need it. And let's continue to have a nice time doing maths together. See you in the next video.